Hi pre-calculus friends, we're in section 6-7. We're going to be graphing other trigonometric functions. Before we get into the deets of this section, I wanted to just talk to you a little bit about kind of remembering some of what we once knew and once discussed around the trigonometric functions. So you know that sine and cosine exist in tangent. We had our SOHCAHTOA. We also remembered that there was a relationship between sine, cosine, and tangent such that sine over cosine of an angle, sine of theta over cosine of theta, is going to give us tangent of theta. And then we remember that there's these reciprocal relationship with these trigonometric functions in blue. The reciprocal relationship is that cotangent is 1 over tangent, or we could also say that it's cosine of theta over sine theta. And then secant theta is 1 over the cosine of theta, and cosecant is 1 over the sine of theta. And so this will help us fill out this chart. If you remember, we filled out this chart and it kind of aligned with our idea of the unit circle. And so, you know, if we were to figure out what the sine of 0 is, the sine of 0 would be 0, whereas the cosine of 0 would be 1. You guys remember? Stay with me. Sine of pi over 6, which is 30 degrees, is going to be 1/2, whereas the cosine of that is the square root of 3 over 2. This should be review. If it's not review and if it feels really challenging, let's talk about it. Let's practice together. And we had like a little neat way of filling out the chart, so you didn't even have to think about it. I'll save that for another time. So anyway, we've got the square root of 3 over 2, and then over here we'd have 1/2. And then finally we get to the sine of 90 degrees, or pi over 2, is 1, and the cosine of that value is going to be 0. And then from there we can get the tangent values. So if the tangent is sine over cosine, as I have up here, if it's sine over cosine, then the tangent of 0 is going to be 0. The tangent of pi over 6 is going to be 1 over the square root of 3, which resolves to square root 3 over 3 when you rationalize the denominator. This will be 1. This over this is just going to be the square root of 3. And what you're going to notice here is that 1 over 0 is going to be undefined. So the reason why we're doing this is to kind of get a little bit of a recollection of what some of the values are of these other trigonometric functions, so that we can understand the graph a little bit better. And so since cotangent is the reciprocal of tangent, the reciprocal of 0 is going to be undefined, because reciprocal of 0 means we're dividing by 0. And then I'll just follow along with the rest of these. If I take the reciprocal of root 3 over 2 over 1 over 2, I'm going to get root 3. This is still going to be 1. This is going to be root 3 over 3. You can see kind of the flip-floppy nature. And then this is going to be 0 because 0 over 1 is going to be 0. Is that making sense, guys? And so what you're going to see is that the values of tangent and cotangent can get really, really large if we were to continue, not just if we were to continue going in between some of these values. If we were to think about it, because as long as you're taking the reciprocal of a fraction, like the reciprocal of 1 over 100 is 100, right? And so even though sine and cosine has a range from -1 to 1, right? Their range is that. These guys don't have the same range, and let's see if we can kind of consider it, even though we're only looking at a finite number of examples. So the secant, as we said, is the reciprocal of the cosine, and therefore the reciprocal of 1 is 1. The reciprocal of this guy is going to be 2 root 3 over 3. I know I'm doing it quick in my head, but I hope it's making sense to you guys. This is going to be 2 root 2 over 2, which just becomes root 2. The reciprocal of this is going to be 2. So you see we're getting some higher numbers. If we were to choose some other values, we would see that the numbers can be even higher. So all of these numbers are 1 or greater. And we're just in the first quadrant, so because we're just going from 0 to pi over 2, or 0 to 90, so we're not getting the full range, but we're just getting an idea of what's happening. And of course the reciprocal of 0 is undefined. So we see in these 3 so far, and we're going to see in 4, we've got these places where the graph is undefined. So that's also new for us in graphing trigonometric function. So let's quickly go through this. This is going to be undefined since cosecant is the reciprocal of sine. This will be 2. This will be square root of 2. This will be 2 root 3 over 3, and finally that's going to be 1. So what you're seeing is that a couple things that I want you to notice. We've got these undefined areas that are going to happen along. We don't have the same range, and so now as we are looking at these graphs, hopefully it'll make better sense. So if we take a look at just the tangent graph and we look at some of the values, you're going to see these red lines are referring to the places where we are undefined. So at pi over 2, at multiples of pi over 2 basically, but not every multiple, at odd multiples of pi over 2, because as you can see, pi is fine and negative pi is fine, which are even multiples of pi over 2. But at odd multiples of pi over 2, you're going to get this undefined value, and that makes sense because that's where the cosine would be 0 and the sine would be 1. So 1 over 0 is giving us these values here. And then you can see what's happening. We've got these undefined spaces are really asymptotes. They're like vertical asymptotes that we've discussed in the past. And so you see you've got this really cool shape. The values where sine is equal to 0 would be the same place that the same place that the tangent is equal to 0. And so sine is equal to 0 at 0, tangent is equal to 0 at 0. Sine is equal to the sine of pi is equal to 0, just as the tangent of pi. And so we have this handy chart that I think you should at least just make sure you understand, if not memorize. The period is pi, which makes sense. You can see that the situation is repeated from here to here, and you can kind of see that the whole cycle happens over and over again. Even though it's not a continuous function, even the whole thing is not connected, you can see that we have the same thing happening over and over again. The domain is the set of all reals except these odd multiples of pi over 2. All right, which is where we get those undefined places. The range is the set of real numbers, so every possible number can be represented as the answer to the tangent of x, as the y value. The x-intercepts are located at pi over n, where n is an integer, so at those values where the sine is 0, and the y-intercept is 0. And over here the asymptotes are defined by these same places that are not within the domain. All right, and then so we can similarly look at, let's see if I can get all of this in here. We can similarly look at the cotangent in the same way. We see that the cotangent and the tangent graph look very similar, except they are they're kind of, I don't know, wiggling opposites, and they're slightly shifted over. Let's see. I'm going to just tuck this in here really quickly. This is one of the branches of the tangent function, and you can see that it's going to overlap the cotangent, where the cotangent is equal to 1 and negative 1, which makes a certain amount of sense because the reciprocal of 1 is 1, the reciprocal of negative 1 is negative 1. The reciprocal of 0, right here, the cotangent in this blue, I'm looking at the blue, cotangent is 0, the reciprocal of 0 is undefined, so that makes sense that that's an undefined place for the tangent function, right? All right, so I just wanted you to kind of see that they're not the same and that they are related, and you can kind of use one to graph the other in a sense. But anyway, let's go ahead and just look at it a little bit. So we have very similar situation as the tangent, however things are shifted and flipped, so we can see that information basically summarized here. The period is pi, that looked right to us. The domain is the set of all real numbers, but now except pi times n, where n is an integer. So where we were doing pi times pi over 2 times an odd integer, this function, the cotangent, is doing pi over n, where n is an integer for its places where it does not exist, or that's not a part of the domain, and that's going to be related to where the vertical asymptotes are, right? They're going to be the same places. The range is a set of all real numbers. The x-intercepts are located at pi over 2n, where n is an odd integer, exactly where the asymptotes were for the tangent line. We've talked about that. There is no y-intercept. You can see that because the y-axis is an asymptote for this graph. And so again, another bit of information that you should kind of have mental access to, if not memorize. And so with that, I started this video before, so I was chatting to you before now, but I'm going to go back to the conversation that I was having apparently with myself. So here's the situation. This is the sine curve, is a dotted line in here, and so what we're using here, and what we often do in order to graph the cosecant, and also we'll do the same thing for the secant, is to graph the sinusoidal curve that it is related to. So here you see the graph of this function here, of the cosine, of the sine function rather. And what I'm going to do is I'm going to lighten that a little bit so it's not prominent, because I feel like it's a little too prominent. It looks confusing to me. So hopefully I can make this look a little bit less less noticeable. If I can, that would be great. If not, that's okay. No, I can't. I was going to try to fade it out by highlighting it in white so it looked a little ghostly, but that's not working. Anyway, focus your attention on the little branches that are coming up from the top here. So you got this guy here. This is the graph of the cosecant function. These U's, they look like little parabolas that are gated in by some asymptotes, right? So again, remembering that the sine function is going to be the reciprocal of the cosecant function, we can use that to graph. So as I'm thinking about this, if the sine is 0, then we're going to have an asymptote. We're going to have a vertical asymptote. We're going to have a place where this graph does not exist. And where is the sine 0? The sine is 0 at every multiple of pi, every whole number multiple of pi that we have, odd or even, or every integer multiple of pi. So that makes sense that we've got those asymptotes there, where the value of the function of sine is 1, the value of the cosecant is going to be 1, because the reciprocal of 1 is 1. You see that, guys? And then same thing with -1, the reciprocal of -1 is 1. So we have these places. And really, honestly, at that point, because we're not going to be drawing super superiorly awesome tight graphs, we can just kind of, we've got the vertical asymptotes, we figure out the places where the value is 1, we're going to draw these parabolic-like functions. They are not parabolas, but we're going to draw these little U shapes inside the boundaries of the vertical asymptotes, and that's how we'll get the graph. That's how we'll get the graph of our cosecant function, and we're going to do the same thing with the secant. So similarly to the other sinusoidal functions that we've dealt with, let's look at this box here. The period is 2 pi. The domain is the set of all real numbers, except the places where sine is 0, which is multiples of pi over n. The range is the set of real numbers greater than or equal to 1, or less than or equal to -1. And so what are they talking about there? They're just saying, hey, you're not going to have any values for the cosecant in between 1 and -1. The values are going to go from 1 to infinity and from infinity to 1. So this would be the range. The range would be -infinity to -1, including -1, in union with 1 to positive infinity. This would be the range of not only the cosecant function, but also the secant function. There are no x-intercepts, there are no y-intercepts. That makes sense. We can look at the picture and see that. The asymptotes are at these multiples, exactly the same places where we've seen this relationship before. And then they give us some information that y is equal to 1, when y is equal to 1, when these values are in coordination, when x is equal to pi over 2 plus 2 pi times n, the integer. What does that mean? So if we think about it, this is going to happen when sine is equal to 1. When is sine equal to 1? Sine is equal to 1 at multiples of pi over 2, or not multiples of pi over 2. Every 2 pi after pi over 2. I'm not saying that right, but what I mean is every full cycle after we get to pi over 2. So we know that 2 pi is a cycle since the whole period is 2 pi. So 2 pi times n, there will be a full cycle where we will always get the sine being 1. If the sine is 1, then the cosecant is 1 as well. And similarly, we can say the same thing, figure out where the sine is a -1, which is going to be at 3 pi over 2, and then when the cycle goes through every full cycle 2 pi, we're going to get another value of -1. The reciprocal of -1 being -1 means that the cosecant is -1. I know I'm saying a lot of stuff. If you need to pause me and just turn my voice off so that you can kind of think through this, I get that, because some of the things just need to be digested in that way. All right, let's go ahead and look at secant. So no surprise, secant starts off with the cosine function drawn in there. And so we've got the cosine function, the highlighted pink is the secant function, and the similar discussion is going to be raised for the secant function, because the secant function is going to be related to the cosine function such that it is same period. It's got the period of 2 pi. The domain is going to be shattered by the places where the cosine is 0, and therefore the reciprocal is undefined, and that's at multiples of pi over 2n. And then that's going to give rise to the asymptotes. Same thing, same argument, same discussion as last time. And so we get these other values that are directly related to the the cosine function as it relates to the secant function. All right, so now let's take a look at example 1. We're going to find each value by referring to the graphs of the trigonometric, that says function over there, trigonometric functions. So if we look at 9 pi over 2, the tangent of that, 9 pi is going to be at 4.5 pi, and my graph that I chose is just off that. But what we can see is that here and if you remember the information that we talked about above, every odd multiple of pi over 2 is going to yield an asymptote, an undefined place, and so that should be no different for 9 pi over 2. So I'm going to try to show it to you on the graph. This would be 3 pi over 2. This right here, this asymptote is going to be 5 pi over 2. 7 pi over 2 is here, and we just barely made it, so forth and so on to the next one, which is 9 pi over 2. And so seeing that, we know that we have an undefined value for that, and that's what we're going with for that portion. If we think about cotangent, the reality is I can pull up the cotangent function. We can look at it and we can do a similar analysis, but I think we can do it without actually pulling up the cotangent, the graph of the cotangent function. Remember the relationship between the cotangent and the tangent function. What's that relationship? The relationship is that they are reciprocals of one another. So what's happening at 7 pi over 2 for the tangent is the reciprocal of that is going to be happening for the cotangent. So if I come to 7 pi over 2, which is right here, we remember the tangent was going to be undefined. The reciprocal of an undefined, because undefined is when you're trying to divide by 0, is just 0. So the cotangent of 7 pi over 2 will be 0. So in example 2, we are looking for certain values of the cosecant and secant function. And so we're looking for theta values that's going to make this true. When is the cosecant equal to 1? So I'm going to start off just like we did before with the sine function, its reciprocal function. So I just draw that kind of sloppy sine function, and I'm going to get my vertical asymptotes in here, and that's going to be here. Anywhere sine is 0 is going to be, the reciprocal of that is going to be a problem for the cosecant. So I'm just putting those in here to give me a good idea of what's going on. I know that this is all happening. This is 2 pi. This has to be pi. This has to be pi over 2, right? And if the sine is pi over 2, then the cosecant has to be, if the sine is 1, then the cosecant has to be 1 as well. So I'm just demonstrating right now. We don't really need all this to answer this question. I'm just demonstrating how I would draw the graph of the cosecant. All right, so now that we have that, we see these values where the cosecant is 1. How can we describe them? Well, we know that that's pi over 2, and we talked about it before. It's going to be every cycle we're going to get this value again. So up here we'll get it again. Up further we'll get it again. How long is a cycle? A cycle is 2 pi. So we know that the value is going to be for all theta such that theta is equal to pi over 2 plus 2 pi n, where n is an element of the integers. Any old integer value will do. That's going to give me a cosecant value of 1. Does that make sense? All right, so we can do a similar thing if we're thinking about the secant. Let's start off with the cosine function. And we know the cosine function does one of these numbers down, and then it comes back up again. And it goes, oh, my calculator, my program doesn't want me to do it, but I am going to do it anyway. All right, so we have that, and then we do it again. Okay, so the cosine function looks something like this. We know that we're going to have those vertical asymptotes where the cosine is 0, but what we're really concerned about here when thinking about the secant function is where the values are going to be -1, and those values are going to be -1 the same place that the cosine values are -1. This should be here. You guys get what I'm doing. I know it's terrible. Stay with me anyway. So we see that it's going to be at multiples of pi, but not at all multiples of pi, but at odd multiples of pi. So this is going to be, the answer is going to give us, let me write this like I want you to see it. Theta is equal to pi plus 2 pi n, where n is an element of the integers. So any integer multiple of 2 pi added on to pi is going, oh, did I do that right? Does that make sense? Let me think about this. Any integer multiple, I said odd multiples of pi. I want to just see if this handles that. Yeah, this does, right? Because if I start off with pi and I add 2 pi, I'm always going to be adding odd multiples of pi. I just needed to check it myself. Thank you for being patient with me, guys. All right, so that can work. I think if you wanted to write any odd multiple of pi, that would work as well as an answer for this one. Yeah, any odd multiple of pi would work as well. So what this little blurb or bit of information is showing us is that you can determine the period of a trig function by looking at that coefficient of the angle theta. And so we've done this before with sine and cosine, but what we're seeing is that it extends to cosecant and secant, which I don't think was that earth-shattering. I think you kind of had that idea. So if you wanted to find the period would be equal to 2 pi divided by k. You know, I write it as b when we write our formula, but whatever. So 2 pi divided by k, Desmos does k, as you guys saw from the last example. All right, so that's going to be the period. However, when you're dealing with tangent and cotangent, since its original period is pi, right? We remember that? Then when I'm looking for the period in this circumstance, it's going to be pi divided by k. And I think that's significant enough for you to hold on to. So in these pink cases where we're dealing with cotangent and tangent, you want to make sure that you are dividing the k value into pi, as opposed to in these values where we're dealing with the sinusoidal functions and their reciprocal functions, we're dividing k into 2 pi in order to get the period. All right, so now that we have that kind of clarified, let's go ahead and check out what's going on. So if we had to graph this, how do we do it? And I know pulling out Desmos is always helpful, but when you're asked to graph, you want to try to make sure you know you can do it by hand and try it by hand. So the first thing I want to do is rearrange this equation so that it looks a little bit more like the way we would want to look at a function. So we're going to factor out the pi over 2, which is the the 1/2, which is the coefficient of theta. So if I factor that 1/2 out, I get theta minus. Now if you think about 1/2 being factored out of pi over 4, you're going to get pi over 2. Does that make sense? Multiply it through with distributive property, you'll see what we mean. And so now we have this function here. So this function is going to show us, we can tell what the period is, we can see that there's a phase shift, and we can see that there's this vertical up and down shift of 2. So that's going to be helpful. So I've taken the liberty to draw in the sine curve, because we know we're dealing with the reciprocal function cosecant of sine. I've drawn the sine curve such that a couple of things are happening. One thing is that this 1/2 gives us, remember we're going to take 2 pi divided by 1/2 in order to get the period, and we get that the period is 4 pi. So I know one full cycle has to happen over 4 pi. We also have this guy here, which is the phase shift, so it's a horizontal shift, pi over 2. I did not do the vertical shift up 2. I will save that in a minute for later, and I'll show you how I'm going to do that. Though I could have shifted it up 2 and then just did the reciprocal function, but I didn't. And so here's what we're going to do. We're now going to draw in those vertical lines where we have asymptotes, because that's not going to change for our function. And you know what? Let's get that out of the way. I'm just going to have these just done in solid lines. I think that'll work out a little bit better. Okay, so I've gone in and I've put the asymptotes in there, and I've put these U symbols in there. And so the next thing we need to do is lift it all up plus 2. And so I'm going to move, if this is at 1, to go up 2, everything needs to go up here to 3. And so that's where this should be. And then we know that these guys need to move up 2, and so these will be at +1. So then our final graph will look more like this. All right, so the dark green is the graph, and I know that this video is starting to get really long. We're going to skip one example. I'm going to do one last example so that I can give you guys an opportunity to try out what we've discussed. So in this final example, we're going to be basically just writing an equation. Write an equation for the secant function with the period of pi, a phase shift of pi over 3, and a vertical shift of -3. So I'm going to write out the generic form. We've got y is equal to sum a times the secant of some b term times theta minus c plus d. And basically we know that we did not get a vertical shift. We got a vertical shift, we didn't get a stretch. So I know that our a value is going to be 1. The b value, which gives us our period, so our period is, in this case with the secant, is going to be defined as 2 pi divided by that b term, or k term as it is in the text. So the period in this case was given to us as pi. So we can therefore see that b has to be equal to 2. Are you guys with me? So therefore 2 times theta minus. So the phase shift is pi over 3. And so we're just going to plug that in right there. And that vertical shift is just down 3, so -3. So finally we get y is equal to the secant of 2. Secant of 2 times theta minus 2. Oh no, that's me distributing it through. I'm not going to do that, but the text will. Your textbook would have this written in this way: 2 theta minus 2 pi over 3, like that, -3. I don't see a good reason for that, so I like this as an answer. All right, okay guys, that was a lot of information, a lot to think about. I hope that it made sense. Let me know if there's some way that I can assist you, and we will talk about it soon. Please take care. Bye bye.